Welcome to Nardar Academy. In this video, we are going to discuss key points in hypothesis testing. A statistical hypothesis is a conjecture about the distribution of one or more random variables. If a statistical hypothesis completely specifies the distribution, it is referred as simple hypothesis. Otherwise, it is a composite hypothesis. See, suppose if we are dealing with a population and a sample, and if we want to make any decision about unknown parameter, then we can make use of the hypothesis testing. Okay, in that case, we make an assumption in the beginning, no, that is called what? Hypothesis. Okay, if that assumption or that assertion completely, that will give you the complete information, it will call simple hypothesis. Otherwise it is called what? Composite hypothesis. Okay, here we have two important hypotheses. One is null hypothesis, another one is alternate hypothesis. Null hypothesis means we usually, null hypothesis is represented by H naught. H for hypothesis, null means 0. Okay, H naught, right? In H naught we usually assume there is no significant difference. Whatever may be the problem, we usually assume null hypothesis as there is no significant difference. Accordingly, we assume our alternate hypothesis. Okay, right. So anything opposite to the null hypothesis is called what? Alternate hypothesis. Now in hypothesis testing, mainly we have two things. One is type 1 error, another one is type 2 error. Type 1 error is rejection of the null hypothesis when it is true. See, the null hypothesis is true, but even if it is true, we are rejecting it, means that probability is called type 1 error and it is represented by alpha. And type 2 error is beta, and type 2 error means it is accepting the null hypothesis when it is false. Null hypothesis is false, but still we are accepting it. That is called what? Type 2 error, and it is denoted by beta. Okay. Then the rejection region of null hypothesis is called critical region, and to the probability of obtaining a value of the test statistic inside the critical region when H naught is true is the size of the critical region. What is the size of the critical region? What is the size of the critical region? The probability of obtaining a value of the test statistic inside the critical region. Okay. When H naught is true is the size of the critical region. So size of the critical region is just the probability alpha of committing type 1 error. And this is also called level of significance. So what are the things we have studied? What is type 1 error, type 2 error, and what is level of significance? Type 1 error is rejecting H naught when it is true, and it is called alpha, and it is also called level of significance. And type 2 error is accepting H naught when it is false, and it is also called beta. Okay, right. Now usually this 1 minus beta, alpha is called the level of significance too, and this 1 minus beta is called the power of the test. Okay, how do we obtain this power of the test? For obtaining this, we have to keep the type 1 error as fixed and look for the test statistic that minimize the type 2 error. That is, type 2 error is what? Beta. We try to minimize beta. That is called what? That is 1 minus beta is there, no? That is called power of the test. Okay, then next one is a critical region for testing a simple null hypothesis theta equal to theta naught against a simple alternate hypothesis theta equal to theta 1 is said to be best or most powerful if the power of the test is maximum. When will you say a hypothesis is best? When the power, that is 1 minus beta, is maximum. Next one is Neyman-Pearson lemma. This lemma states if C is a critical region of size alpha and K is a constant such that L0 by L1 is less than or equal to K inside C and L0 by L1 is greater than or equal to K outside C, then C is a most powerful critical region of size alpha. Okay, this L0 is the product of f of xi theta naught, that is the density functions. Okay, and L1 is equal to product of f of xi comma theta I, right, theta 1. Now the power function pi of theta is defined to be alpha of theta. Okay, when theta assumed under H naught, and it is equal to 1 minus beta of theta for theta assumed under H1, and the operating characteristic curve OC curve is given by plotting the values of theta and pi of theta. Okay, now see, testing of hypothesis H naught, the null hypothesis theta equal to theta 1, and the alternate hypothesis is theta is not equal to theta 1. This is called two-tailed test. See, the null hypothesis says there is no difference between theta and theta naught. And if you take alternate hypothesis as theta not equal to theta naught, it is called two-tailed test. Okay, in this case, modulus of x bar minus mu naught is greater than z alpha by 2 sigma by root n, that is x bar is less than mu naught minus sigma alpha by 2 sigma by root n and greater than mu naught plus sigma alpha by 2 sigma by root n. So if z equal to x bar minus mu by sigma by root n, then z is less than or equal to minus z alpha by 2 and greater than z alpha by 2. See, this is the critical region. See, here this is the normal curve and this is mu naught, and accept h naught in between mu naught minus, in between these two values, that is mu naught minus z alpha by 2 sigma by root n, mu naught plus z alpha by 2 by sigma by root n, and these are called rejection region, rejection of h naught. Okay, right. Then testing of null hypothesis, theta equal to theta naught against theta less than theta 1 less than theta naught or theta greater than theta naught is called one-tailed test. See, previously the alternate hypothesis we have assumed theta not equal to theta naught. In that case, either theta may be less than theta naught or greater than theta naught. In that case, both left and right sides will come. Here we have assumed the alternate hypothesis either theta less than theta naught means this side, greater than theta naught means this side. This is called one-tailed test. Okay, so the corresponding pictures are given here. So this is the hypothesis for theta less than or mu less than mu naught, here for mu greater than mu naught. Okay, corresponding to the observed value of the test statistic, the p-value is the lowest level of significance at which the null hypothesis could have been rejected. Okay, I am not going to do the problems here, only the concepts are discussed in this video. In the similar way, for difference between mean, we use the test statistic z equal to x1 bar minus x2 bar minus mu1 minus mu2 by square root of sigma 1 square by n1 plus sigma 2 square by n2, where x1, x2 are sample mean and mu1, mu2 are population mean, sigma 1 square, sigma 2 square are population variance. Okay, for small samples and when sigma 1 and sigma 2 are unknown, okay, when the population standard deviations are unknown, we make use of t-test. For t-test, what is the formula? x1 bar minus x2 bar minus mu1 minus mu2 by s into square root of 1 by n1 plus 1 by n2. This s square is equal to n1 minus 1 s1 square, that is the combined standard deviation or the combined variance, plus n2 minus 1 s2 square by n1 plus n2 minus 2. Okay, and then for variance, okay, given a random sample of size n from a normal population, to test the null hypothesis, sigma square equal to sigma naught square. Okay. Based on the sample variance s square, we use chi square equal to this parameter we have to choose chi square equal to n minus 1 s square by sigma naught square. For testing equality of variance of two normal population, consider a random sample of size n1 and n2 from two normal populations with variance sigma 1 square and sigma 2 square. Then f equal to s1 square by s2 square, that follows f distribution. So we have seen where to use t-test. Okay, here z and here f. Okay, that's all. Thank you.